Now we come to the manufacturing processes. I will start with the aluminium one, and then I will go to the gray cast iron one. Now what you can see is that the parts we have for this pump, of course this one is going to have less seals, and the part is actually going to be shorter than the other one. Mainly for this part, for this pump we're going to have the main body, the top part, which is going to be the cap, two shafts, cross plates, and of course within we're going to have four pushes which are going to be inserted inside the body, which is going to work as a bearing parts. Let's start to inspect the parts one by one, and during that we're going to do the measurement process. So I will put the shafts aside, and I will start with the main body and the top part. Inspect the shape of the part. It's look like a complicated shape. The question is, can I do this one by the die casting operation? The answer is going to be no. We have two different levels, and to have the support which is going in the third dimension, and this will make it very hard actually if we're going to do this one by the die casting operation. As an engineer, you should have the judgment. If I'm going to take a look to the part, if I'm not going to have actually any what we call nipples, actually that means that we don't have any injection for this part. Instead of that, if we're going to have a line, symmetrical line in the middle, that means this part has been done by the casting operation. Actually, you can see this being removed here by certain type of the machining. So this part has been done basically by the casting operation, and I have to be specific, it's done by the sand casting operation. Remember that in the sand casting we're going to have the box, and we're going to divide the box into multiple layers, mainly two layers. We're going to call it the cup and the drag. The cup is going to be the top part, and the drag is going to be the lower part. We start with making the pattern. Now we go to another division for the pattern. If I'm going to make the same part, like this whole part as a pattern, then I can simply do it that way. I'm going to put this one inside the sand to the half level, compact the sand around it. Of course it's going to be compact on the top, compact the sand above it, and I'm going to remove the sand, remove the part. I'm going to have the cavity which representing the top side of the pump, this part inside the cup. Repeat the same process for the drag, and when I'm going to put the two halves, I'm going to have the full cavity of this part within the mold. Now what do I need to put is, I'm going to have these two cavities. The holes is going to be solved. Actually I'm going to draw this one later. So we have these cavities, so I have to put something called the core. The core is actually going to be a dried sand. I'm going to put it inside the cavity of the mold, and we're going to of course do a certain machining for the part later after removing the core, to have the exact dimension of the geometry we have. Now one of the things you have to remember are well, actually two things. First, that the pattern should be oversized because we're going to have shrinkage. The cores should be undersized because we're going to have the machining to enlarge the cavity we're going to have inside. So the pattern is oversized, the cores are undersized. Do the casting operation, take the part, clean it from the sand, use some vibration to remove the core inside, and we're going to start to do a machining process on that. Face milling, boring to enlarge the diameter, drilling of the holes, through holes, drilling, and then we need to do a reaming for the dowel positions, dowel holes. You can see actually dowel holes are going to be blind holes, the diameters for the through holes for the nuts should be larger than the diameter of the nut, because the bolts, because the bolts should move freely inside this hole. The same thing from the other side. We are going to do some milling operation, face milling, and we are going to do the profile cutting here to have these two-level geometry. Okay, cylindrical shape. Done. We finish with this part. Now the inspection of this part before we are going to do the machining is you are going to take a look on the part, see if we are going to have any cavities on this side, if we are going to have any misrun to fill the whole cavities. Usually if we are going to have higher pressure, high speed, high vibration, we tend not to fix the part by adding the metal by the welding operation. Instead of that, we recycle it, get a new one. How to avoid all these problems? You can simply be sure about your calculation for the pouring temperature and the pouring velocity for the metal during the casting operation. Another thing we have to think about, I can make the pattern out of wax, and this will be the invest casting operation. Just remember, for the invest casting operation, we're also going to have the pattern which made of sand. So in all the cases we're going to be, the core is going to be made of sand. So in all the cases, you know that the invest casting at the end is going to go through the having the shell on top of it, and this shell will be supported by some sand on the side to hold itself. Now we're going to the main body. Exactly the same process. So we are going to have the pattern which look like that shape, a little bit oversized, and then we're going to put some cores inside to have the internal cavities. So you can see actually that some of the holes here is going to be through. So actually we're going to have a complicated shape for the core, but at the end it's not going to be that hard to do it. One of the processes we can do is that we can use the two different wax melting temperatures, and we can have the cores and the main body made by the same step. So for example, we can make the pattern at the top is going to be done by a wax with higher melting temperature. The core one is going to be the wax with lower melting temperature. We put them one after the other. You know that the wax actually is going to be made, the pattern is going to be made by the injection molding process. So we start to heat up the part. The internal core will be melt, and we are going to spray the internal side with the ceramic, leave it to solidify. Okay, then we are going to have the wax pattern with a layer of the ceramic inside. Then we are going to immerse it in the slurry ceramic, and we are going to have the outer shell to be solidified, and then we are going to have the cavity here to be filled with the molten metal, and then we're going to have the hole pump with the cavities inside. Again, we need to do the face milling operation, the drilling and the tapping, because these holes actually are going to be threaded. The double holes is going to be drilling, and then we're going to do the reaming to have the exact dimension. And on this side we are going to do the face milling, boring operation, and the internal threading. You can see we have some internal threading inside, and this can be done on the milling machine. For this side, after we did the face milling, we can take it to the reaming machine, to the boring machine, to increase the diameters of these two levels. And of course we need to do some face milling to the inside layer here to have a good surface finishing. We can do actually everything on the milling machine. If we're going to have a cutting tool, which is going to have a multiple stage, costume one, the cutting tool will be fixed here and on this double. So this cutting tool will be rotating on the milling machine and getting inside. So in its movement, this cutting tool will be cutting that wall. and then at the end is going to do the face milling for this level. The smaller cutting tool will do the same work for the bushes housing inside, and thus I can do the whole operation in single go. So just one cut, the cutting tool will go inside, and then it's going to do the internal boring and the face milling for the lower level for the two stages of the we have inside. Now we finish with the main body and the cab. That's how we made them. Going to the dowel. The dowel is a steel bar with a certain diameter. Let's say that the diameter, so I can turn on the lights. Let's have a motion sensor. So we're going to have the bar with 10 millimeter diameter, for example, and then I'm going to do a good service finishing for it. This can be done by the grinding operation by running it between the two supporter, and of course going to be the cylindrical shape external grinding operation. Have the good service finishing for it, and then I will, of course, the dowel holes here is going to be drilled and reamed to the diameter of 9.9 millimeters. So when I get to insert the dowel inside, it's going to be fetid press. After we got the good surface finishing, we can simply cut it into a small pellets, and these pellets are going to be fixed, one dowel on the top side, the other dowel is going to be on the opposite direction on the lower side. So it's always going to guide me about the best location or the correct location of the cap on the main body. You can see that how close the dimensions are. So now it's hardly to take the part off. I need to use some movement. One of the reasons is that actually this pump, the dowel actually has been rusted because it hasn't been used for a while. Now we're going to the shafts. We have two shafts here. One of the shafts is called the master. The other one is going to be called the follower. Or I can call it master and the stage. It's up to you. You can see that actually that I can move these two gears together because it have very high tolerances between the gear teeth. Also, we have a very high tolerances for the diameter of the shafts here. This should be made to a very high tolerances, otherwise the two faces will be stuck, and also for the side because it's going to be stuck inside the pushes. Okay, now it can move freely because have very high tolerances between them. Always should be minus. So when I'm going to have the diameter to be 45 millimeter, for example, I expect that the dimension should be put on this side should be 45 minus 0.05 millimeters. Okay, minus. Otherwise, we are going to have the interface between them, and this will stop the shaft from turning inside the pushes. The shaft is going to be machined on the turning machine. You can see that we have multiple levels. We have two sides because what we have here is small diameter, larger diameter than small diameter. All the cases, it's impossible to do that in a single cut. I cannot hold the part like that and start to use my cutting tool, okay, to cut the 4 stages at once. Because usually the cutting tool is going to be either right-handed or left-handed. That means it's going to be the left-handed one, where it's going to start cutting from the right to the left. It cannot cut backwards. And it's not going to be cut that way because this will miss the cutting of that face. So we need to do the cutting by using 2 stages. Stage number 1, these 3 diameters. Then turn the part and do the cut for the stage number 2. Always going to use the steel bar to do that. The steel bars usually is not going to be a custom made. We're always going to get them as a standard dimensions. So to get the standard dimension or the bar we're going to start work on, we need to check what will be the maximum diameter we have for this shaft, which is going to be for the gear. For this one, need to use the glasses. Okay, now for the maximum diameter I can have for this part is going to be equal to 61 millimeters. So for the 61 millimeter diameter shaft, we need to start with the diameter for the cylindrical part we're going to start working on. We call it the bar. Should be anything above 61. So actually the standard we have is either 60 or 65, so we'll go the 65, start to cut it down to have the 61 millimeters. Go back to this session I recorded last Tuesday, and you're going to have more details about the cutting operation and how to remove the material to have the final shape. Same thing will be done for this part. Okay, now after we cutted the multiple levels, you can see that here we're going to have a small cylinder, larger cylinder, and smaller cylinder. We did it by holding the part from here first, do the cut for these 3 stages. Now we turn back, we did the cut on this stage, done by the turning operation. In certain of the cases, if you're going to have a new project and you think that actually increasing the production rate is going to be a matter, then you can use the twin spindle machine that can do the cutting in a single loading up. You have to think about the manufacturability is that you're always using what you have. You don't have to put a high investment in new machine that you're using for a single job only. So for the after you're going to have the cylinder with multiple 3 stages after 4 stages after the cutting, you need to prepare it for the cutting of the supply and the cutting of the gears. Actually, the supply and the gears can be cut together on the milling machine. We have to hold the part. Actually, that's why we have these 2 holes. We hold them between the centers on what we call the indexing device. The indexing device is going to divide the circle into an equal number. It's not degree, equal numbers. So, for example, I'm going to divide it to 1, 2, 3, the number of the grooves we have. So we put on position number 1, the cutting tool will be passing it through and cut the teeth number 1. Second position, gear number 2, 3, 4, until we're going to have the whole number. The same thing here, I'll show you the video on the on Tuesday session. Now the gear has been cut to the shape, and after that we need to send it for the heat treatment, because the too much forces we added through the cutting operation on the milling or the turning operation is going to keep something we call the residual stresses inside the shaft, and that the heat treatment will remove these stresses from the shaft. We did that. We need to do the grinding operation. So the grinding operation, grinding the teeth of the gear, take it to the exact surface finishing and the good dimension. The same thing for the shaft here and for this part as well. So the maybe it's going to require to coat it with a certain metal like nitrizing or decarbonizing or whatever the process is. This can be done as well to the part by exposing it to a stream of nitrogen at under a certain temperature, and this will give it a high strength for the surface, and this will make it last longer. The same process actually is going to be repeated for this part. The dimension actually, as you can see, are the same, so the process is going to be the same, but we don't have the extended length of the supply. Now this supply is going to be connected to the motor or the gearbox, which is going to move the pump. So we have the thruster plate, and this thruster plate is going to be made by the stamping operation. We're going to have a plate with this thickness, and we're going to stamp it by using the die, and we're going to have the part directly. This process can be can be done multiple times within 1 minute. This is going to be feeding the sheet and stamping multiple times. Something like the technology you use to make this ruler. It's made by a standard operation. Alternatively, if you would like to make one part here, we can do it on the milling machine. We just put the plate on the milling machine and then we start to cut it. We can do it with a laser cutter as well. Okay, if you're or plasma cutter, if you're going to have the good machine, laser cutting machine that can cut the metal with this thickness. Okay, so that's all for the pump number 1. We're going to go to the pushes. The push is going to be a sheet metal, which is going to be rolled, and then it's going to be molded, seam molding from one side. And during this operation, we are going to actually coat it by spraying the Teflon layer on it, and this will give it the ability to retain the oil within the bushes. Okay, so the next video is going to be about the other pump, and the last video is going to be about the dimensioning before we're going to go for the possibility of the design for the manufacturing and design for the assembly.